All right, you guys, welcome back. Usually it gives me a little chime when it's actually recording, but I didn't hear it do that. Okay, I'll just get started here. Okay, definition of continuity at a point. This should be in your WUBI as well. I don't know if you need this much detail. This is probably the piece that you need to have in your WUBI. You need to memorize this, and they will expect you to know it. And so, and so will I. So, what we're talking about is you have a function at some point C. And the question is this function continuous at this very point? And by looking at a picture, it's obvious if it's continuous or not, right? If you have a picture that looks like this, obviously that's not continuous. But how do you put this in a math terminology that we can actually execute it and go through the steps? And so what they do is they have three conditions, and they're pretty straightforward. Number one, f of c exists. So for me, what that means is you should be able to write the value of the function at x equals c using function notation and an equal sign. And remember, the equal sign is the most important symbol in all of math. It's the most powerful symbol in all of math. So for instance, if you wrote f of 4 is 7, what you're saying is when x is 4, the function's value is 7. Okay, so to avoid getting in any trouble in this class, please never use the equal sign in combination with anything infinite, undefined, or anything that does not exist. Just avoid it, okay? Your textbook does it from time to time with limits, and I just wish they would not do that. Some people do it. I'm telling you, if you avoid using the equal sign with infinity, you will avoid a ton of problems and issues that can come up, okay? So suppose you have a function that goes off to infinity. Just write down, instead of writing f of 4 equals infinity, I really frown on that. Instead of doing that, just say it DNE. DNE is an abbreviation for does not exist. Just say f of 4 does not exist to signify it doesn't exist. And if you feel guilty saying it does not exist because you know it's going off to positive infinity, you can say that. You can say f of 4 goes off to infinity. It approaches infinity if you want to, and that's fine. Now everybody knows what we're talking about without having to use the dreaded equals infinity. Okay, and here's why I'm biased against using infinity. Infinity is really a concept as opposed to a specific. It's not a specific value. If you ask someone what's the first digit of infinity, is it a 1 or a 9 or a 3? It's a meaningless question. And so you end up with silly things like this. Most people would agree infinity plus 1 is equal to infinity. I mean, why not? Okay. But again, we got ourselves into trouble here because we're using infinity as if it were a finite set number, or not a finite number, but a set number. And so the problem with this logic is you end up immediately, by doing perfectly legitimate algebra, you end up with 1 equals 0. Okay, and we know that that is not true. And so there's a contradiction somewhere in our thinking here. And where's the contradiction? Well, that's a whole philosophical question that you'll get into. But basically, the mistake you made is you used infinity as if it were a number, and you just can't do that. So I would avoid at all costs using infinity with an equal sign, and it will just save you a tremendous amount of trouble. Okay. All right, second condition is that you have to show that the limit as x approaches c. So when you approach from the left and when you approach from the right, that limit does in fact exist. If they're different, that limit doesn't exist, okay? And so you may need to evaluate the limit to satisfy it. And sometimes you have to do both a left and a right-hand limit. And this is the one that students forget by the end of the year. They're pretty good about it the first semester, and then it kind of falls off. And by the end of the year, they forget that. You have to do the limit in both directions. Especially if the function is defined piecewise, then you have no choice, okay? And just so you know, there are 8 methods for evaluating limits, and we'll continue developing them throughout the year. But basically, substitution is the easiest one of all. You just plug the value of c into the function and hope that you're not dividing by 0 or something like that, and then you're fine. So usually you just substitute the number in and you're fine, okay? All right, and then finally, what this last condition says is, hey, look, the limit you get has to equal the value of the function. It basically is saying these two actually have to be equal. And remember, you guys, I only use an equal sign if I have a finite number here and a finite number there. I never use the equal sign, infinity equals infinity. If you never do that, you'll never have to worry about this if it's continuous or not, okay? So this just says that the value of the function from condition 1 must be exactly equal to the value of the limit from condition number 2. Okay, so here's an example. This is a piecewise function. And you guys, if I graphed this, you would immediately see what's going on with this function, and you'd see the deal. But the reason I'm putting it like this is so that we can talk about this in terms of the definition of continuity. So the first thing is it continuous at x equals 5? And so the first condition, number one, is we just have to say f of 5 is equal to, and if we're able to write something down there that's right, we're fine. So according to this piecewise function, when the x is 5, the value is 26, and so we are done. Okay, so f of 5 exists. There, we're done. Okay, condition number two, we have to evaluate the limit as x approaches c of f of x. Now that's a little bit different. We have to consider that we approach from the left, and we also need to approach from the right. Okay, so I really need to do two limits. I have to evaluate the limit as x approaches 5 from the left of f of x, and I also have to evaluate the limit as x approaches 5 from the right of f of x. Oh, it's not f of x, it's h of x, isn't it? So back right up, I made a mistake. H of 5 and h of 5 exists. Okay, this is general terms. Up here is in terms of f, but in this case, they gave us function h, so I want to use the notation correctly. So I have to evaluate these functions. There we are. Okay, so well, what is the limit as x approaches 5 from the left of h of x? Well, fortunately, when x is less than 5, we use this. And so we can use the equal sign here and simply plug in a 5 for x, like so. Okay, and there we have it. This is equal to 25 plus 2, 27. Okay, now those of you that are on your toes will recognize we immediately have a problem here, that this does not equal this, but that's condition 3. So for now, I'm just focusing on condition 2. Okay, in this case, if we approach from the right, I can just use substitution, and so I can literally just write that this is equal to 6 times 5 minus 3. Substitution is the best method for evaluating limits, and I don't get into any algebraic trouble here. 6 times 5 is 30 minus 3, otherwise known as 27. And so because these both match, therefore, this little pimply triangle thing here, it means therefore the limit as x approaches 5 of h of x is equal to 27, because these both match. If they didn't match, you wouldn't write that. You'd say the limit does not exist. But in this case, they match, and there we have it. Okay, and then finally, condition number 3, what we're looking for is it true that the limit as x approaches 5 of h of x, is that actually equal to h of 5? And that's the question we have to answer. Well, we just evaluated this a moment ago. We said the limit of this was 27, and is that equal to h of 5, which we earlier wrote down was 26, and we have a problem here. They're not equal, okay? So basically what we're saying here is, if you look at the graph of this thing, you know, as you get closer to 5, sorry, you guys, I'm off the screen. So as you get closer to 5, we basically have a linear function. We have a linear function as we approach from the right going in. Okay, and then at 5, oh, and that's at 27, right? And then at 26, we have the value of the function there. And then at that point, this thing extends off like so. So basically, we have what's called the removable discontinuity. There's just a point discontinuity in this thing. At 5, this thing bounces around. And so therefore, the function h of x is not continuous at x equals 5. So pretty straightforward. These two things don't match. Okay. So what I'm emphasizing here is using the equal sign for finite numbers. Okay. When you evaluate a limit, they do condition number 2 here. They say this limit exists. You almost always have to do the left and the right limits, almost always, okay? Left and right-hand limits. Okay, and then finally, that those two things are actually equal. And so there you have it, okay? All righty, guys, I think you're set and ready to do the homework, okay? All right, you take care. I'll see you in class. Bye-bye.